All right, so moving right along through Unit 3, talking about chemical bonding. So far, we've had a pretty decent introduction to ionic bonding, when electrons are transferred from one atom to another to create those oppositely charged ions that then stick together. We've also had a pretty decent introduction to covalent bonding, where you have electrons being shared in between atoms, right? And in both situations, the goal was to satisfy the octet rule, or I guess to put it more technically, reach the electron configuration of a noble gas element, right? What we're going to learn today is that while there are sort of two fundamental categories of chemical bonding, the real story is something a little bit more, there's a little bit more gray area involved, okay? And so we're going to get into this concept of electronegativity, and we're going to learn about what a polar covalent bond is as we discuss this. So your objective for today, two things really. The first one is pretty simple. We're going to be able to define electronegativity, figure out what this is, and identify its trends on the periodic table. We're also going to be able to determine the type of bond formed between atoms based on the atoms' electronegativities and the difference in their electronegativities. Okay, and we'll get some practice with this towards the end of the video. Okay, so first of all, what is electronegativity? This is a property that an atom or an element has. It's given a number value, okay? That number is a measure of the ability of that atom in a chemical compound to attract electrons from another atom in the compound. Let me say that again. It's a measure of the ability of an atom in a chemical compound to attract electrons from another atom in the compound. Elements with higher electronegativity values are able to pull harder on shared electrons than elements with smaller electronegativities. Okay? So, let's think about this for a second. What could make an element more or less electronegative than another element? What could give an element or an atom, what could make it good at pulling at electrons, and what could make it bad at pulling on electrons? And to look at this, to sort of uncover what the secret is here, we're going to look at a couple of examples, okay? So we've got two elements here, sodium and chlorine. This is example number 1. The question is, which of these two elements likely has the higher electronegativity? Remember that high electronegativity means good at pulling on electrons. Low electronegativity means bad at pulling on electrons, okay? And so to talk about this, what I'm going to do is I'm going to do two little quick sketches, okay? And I don't want to spend too much time on this, but I'll do two quick sketches here. We'll look at some Bohr models, okay? And I'm not going to fill in all of the electrons, but I will fill in a couple. So here's sodium, here's chlorine. Here's the 1 valence electron for sodium. Chlorine has 7 valence electrons. And you probably remember us talking about this previously. Sodium and chlorine, we talked about this being an ionic bond, where this electron here sort of flies off and goes over to chlorine. And what you end up with are these oppositely charged ions. They're attracted to each other. It's an ionic bond, yada, yada, yada. Well, the question that we want to ask ourselves today is why? Why does that electron move over from sodium to chlorine? And the answer is actually pretty simple. If you look at the periodic table, do a quick sketch of a periodic table here. Here's sodium, and here's chlorine. Okay, they're in the same row on the periodic table, row number 3. Sodium is over here on the left-hand side. Chlorine's over here almost on the right-hand side. Sodium is number 11, and chlorine is number 17. Sorry, they're in the second row. Or no, sorry. I've drawn this a little bit poorly. They're in the third row, so technically there shouldn't be any. It doesn't matter. Anyways, so sodium's on the left side, chlorine's on the right side. So the question is, right, why does this electron fly over to chlorine? And the answer is this right here, their atomic number. The atomic number is the number of protons, right? Chlorine has more positively charged protons in its nucleus than sodium does. Therefore, chlorine is better at pulling on electrons, or pulling on this electron, than sodium is. If you remember us talking about ionization energy, electron configuration is kind of like ionization energy. Okay? Remember, ionization energy was the amount of energy it takes to remove an electron. Well, it does not take a lot of energy to remove an electron away from sodium. Okay? It doesn't have a very good hold on that electron there, whereas chlorine, it takes a lot of energy to move these electrons away, and chlorine has a really high electronegativity. It's able to easily pull that electron away from sodium and steal it completely. Okay, so yeah, there's that. Let's look at another example here: beryllium and oxygen. So I'm going to clear this out a little bit. Do another little quick drawing here. Here's beryllium. Here's oxygen. Okay, so I'm not going to draw all the electrons, but I'll draw a few of them, the outer ones. So beryllium has 2 valence electrons, oxygen has 6. All right, so the question is here, what happens? Which of these elements is likely to have the higher electronegativity? Well, beryllium's number 4, oxygen is number 8 on the periodic table. There's more protons in the nucleus for oxygen than there is in the nucleus for beryllium, so oxygen is going to be the one that has the higher electronegativity. It's going to be better at pulling on electrons than beryllium is. Okay, so once again, if I look at my little sketch of the periodic table here, the winner is oxygen, which is over here. Okay, and then if we look at aluminum and phosphorus, I'm going to skip the drawings. Okay, but aluminum and phosphorus, it's going to be the same situation, number 13 versus number 15. The element with the higher number of protons is going to win. Okay, they're in the same row. So aluminum is also over here, or sorry, phosphorus is also over here on the right side of the periodic table. So what we're noticing, right, can you describe a general trend of electronegativities? Elements over here on the right side of the periodic table tend to have higher electronegativities. They're better at pulling on electrons than those on the left side because they have more protons in their nucleus. Okay? So, as you go across a period from right to left, from left to right, electronegativities tend to increase. Okay, that is the period trend. All right, as you go from left to right, electronegativities tend to increase. Okay, let's look at some examples where you have elements in the same column. Okay, so here we've got fluorine and bromine. So once again, I'm going to draw my Bohr models here. Fluorine, relatively small atom. Okay, bromine, much bigger. Okay, now the valence level for fluorine is the second energy level. The valence level for bromine is the fourth energy level. All right, these are in the same column. Okay, so if I look at my little sketch of the periodic table, which I seem to get worse at drawing each time I do it. There we go. So fluorine and bromine are in this halogen column. Okay, F is up here and bromine is down here. These have the same, they're in the same column. Okay, so we could think of, okay, well, bromine clearly has more protons, right, because bromine is number 35, fluorine is only number 9. But there's another factor at play, and you may remember us talking about this when we talked about ionization energy. The fact that there's all these extra layers of electrons that are engaging in this electron shielding effect, that actually turns out to be the dominant factor. If you remember us talking about ionization energy, it was actually easier to take electrons away from bromine than it was from fluorine. Even though it has more protons, even though it's got a higher nuclear charge, the increased distance from the nucleus, right, remember Coulomb's law, the increased distance from the nucleus coupled with the electron shielding effect results in bromine actually having a lower electronegativity than fluorine. Okay, and I'm not going to go through all of this, all these examples, because I do want to respect your time, and I've got quite a bit more to get to in the video. But long story short, elements that are at the top of the periodic table, towards the top, tend to have higher electronegativity values. Their nuclei are better at pulling on electrons than larger elements, and that is due to the electrons actually being closer to the nucleus and not having as much electron shielding going on. Okay, so long story short, what is the group trend? As you go bottom to top, or here I can actually write this a couple of different ways. As you go from bottom to top, so as you go from as you go up the table, as you go up the table, electronegativities tend to increase, or right as you go down the table, they tend to decrease. Okay, so you can think of it either way. All right. And here is an actual chart that has the electronegativity values on it. Okay, and we're going to use a chart that's probably very similar to this. I'll give you a link to this in Canvas somewhere. But as you can see, the element that is the furthest to the right and the furthest up on the periodic table, meaning fluorine, right, and sort of in the top right corner, it's got the highest electronegativity value of any element, 4.0. Okay, it's kind of like a grade point average. Okay, it's got the highest electronegativity value. The element in the opposite corner, so all the way to the left and all the way to the bottom, francium, has the lowest, or tied for the lowest, electronegativity value. Okay, and so those are the trends. Okay, as you go from left to right, things go, electronegativity gets bigger, and as you go from top to bottom, they get smaller, or bottom to top, they get bigger. Okay. All right, so what does this matter? Why do we care about this? Well, it turns out that the type of bond that gets formed between two atoms basically depends on this electronegativity, okay, and specifically the difference in electronegativity between two elements, okay. If the difference in electronegativity between two elements is very large, so say greater than or equal to 1.7, the bond is going to be an ionic bond. One atom pulls much harder on electrons than the other, and so the electrons are going to be transferred. Okay, so that is a situation like this, where you have sodium and chlorine. Chlorine has a much higher electronegativity. I believe its actually we can look this up. Its electronegativity is 3.0, and sodium's is only 0.9. Okay, so the electronegativity value is 3.0 for chlorine and 0.9 for sodium. The difference in electronegativity, that's what this stands for here, okay? The difference in electronegativity is 2.1. We would call that a large difference, okay? What that means is that when these two atoms engage in a chemical bond, chlorine is able to completely strip that electron away, okay? Sort of steal that electron away. Chlorine is much better at attracting electrons than sodium is. And so you end up with an ionic bond where electrons have been transferred. Okay. The flip side of this is a covalent bond. Okay, and this occurs when you have a difference in electronegativity that is really small, less than or equal to approximately 0.4. Okay, and a really great example of this would be, let's take two chlorines. Okay, let's say we have two chlorine atoms. They're both going to have the same electronegativity, 3.0 and 3.0, so the difference between these is 0. There is no difference in their electronegativity. Both atoms pull equally on the electrons, and so in order to reach that, in order to satisfy that octet rule, right, to reach that electron configuration of a noble gas, they're going to share these two electrons between them rather than one stealing it away from the other, right? And so in this situation, electrons end up being equally shared, and that's what we call a covalent bond, okay? Now, the whole reason we bring this up is because there is a situation in the middle, right? What happens if your difference in electronegativity is moderate? In between these values, right? Between 0.5 and 1.6, what happens there? Well, this is called a polar covalent bond. It's still a sharing of electrons, but it's an unequal sharing. This situation here is an equal sharing because these two atoms have identical electronegativities, right? The difference in electronegativity is 0. But if you have, say, water, okay, so let's look at water. Oxygen has an electronegativity of 3.5, hydrogen 2.1. What's the difference there? 1.4, right? This is in the high end of the difference in electronegativity being moderate, leaning towards, right, an ionic situation. This sharing of electrons here and this sharing of electrons here, that is not an equal sharing, okay? The hydrogens are not as good at pulling on the electrons as the oxygen is. The oxygen is highly electronegative, okay? 3.5 electronegativity, second highest electronegativity on the periodic table. The oxygen, much, much better at pulling on those electrons, okay? So what does that mean? Okay, what does it mean for electrons to be unequally shared? Well, let me show you, okay? I'm actually just gonna, I need a little bit more space here. We're just gonna do one of these examples. We might do another one here if I have time, but we're gonna look at water again, okay? And let me draw this a little bit more neatly for you, okay? Okay, so I'm gonna connect these lines here, right? We've satisfied the octet rule for oxygen, satisfied the duet rule for hydrogen, but what we've established, right, is that the electronegativity difference across this bond and across this bond is 1.4, right? That's the difference in electronegativity across each bond. That means that each bond, which represents 2 shared electrons, right? Each bond represents 2 shared electrons. Those 2 electrons are not being equally shared between the 2 atoms. Instead, they're getting pulled closer towards oxygen because oxygen has the higher electronegativity. Electrons are negatively charged, right? So what this ends up resulting in is a partial negative charge on the oxygen atom and partial positive charges on the hydrogen atoms, okay? This is called a polar covalent bond, where you have 2 poles, kind of like a north and a south pole with a magnet, okay? You have 2 poles, a negative pole and a positive pole, across each bond, okay? And this occurs, once again, when you have differences in electronegativity that are moderate, somewhere between 0.5 and 1.6, roughly, okay? Let's look at one more example, okay? Let's look at this chemical here, ethanol, okay? Actually, that is not ethanol, that is methanol, all right? So let's look at methanol, all right? Let me clear this out. A little bit of a typo there, I'll fix that. Okay, so this is, one of those ways to write these formulas. CH3 is going to be something like this, okay? And then the OH, this is an alcohol group, okay? So the question is, right, we want to draw these structures, we can do that. Label any polar covalent bonds. Okay, so we need to determine, are there any polar covalent bonds? And if there are, we need to label them with those partial negative. This is kind of like a music note, okay, and partial positive labels, okay? This is actually the Greek letter delta, lowercase delta, okay? This is capital delta, okay? This is lowercase delta with a negative and positive sign. Okay. So we need to look at the electronegativity values. I'm going to actually label those on here. It's 2.1 for all the hydrogens, 3.5 for oxygen, and 2.5 for carbon. Okay? And just to give myself a little bit of space to work here, I'm going to redraw this and put some actual labeling on here. Okay? So, where do we have polar covalent bonds? There's 5 total bonds. Okay, I see the 5 lines. We want to look at each line, determine the difference in electronegativity across that bond. If the difference is moderate, okay, meaning greater than or equal to 0.5, basically, then we're going to call that a polar covalent bond. If it's not greater than 0.5, that's going to be a regular covalent bond. We're going to assume that the electron sharing there is either perfectly equal or close enough to being perfectly equal, to where we don't have these partial charges. But if we do have a difference in electronegativity greater than 0.5, okay, that's when we're going to say, okay, this is a polar covalent bond and we need these labels. All right, so let's look at the carbon-hydrogen bonds first. We have one here, and one here, three identical bonds, carbon to hydrogen. The difference in electronegativity between carbon and hydrogen is 0.4. This puts it into the small category, meaning non-polar. It's just regular covalent. That means we don't need any partial negative or partial positives on here due to those bonds. Okay? Let's look at the carbon-oxygen bond, 2.5 and 3.5. Well, the difference there is 1.0. This does fit into that moderate category, right? This is greater than 0.5. So that means this bond here, these two electrons, these are not being shared equally. They are getting pulled closer to one element than the other. Which element are they getting pulled closer to? Oxygen. Oxygen has the higher electronegativity value. And because electrons are negative, okay, electrons are negatively charged, the oxygen atom is going to be the one that's partially negatively charged, whereas the carbon atom is going to be partially positively charged. Okay? So when you determine that there's a polar covalent bond, it's across that bond that the two poles arise. Okay? All right, the last bond we need to look at is the oxygen-hydrogen bond. We saw that with water, right? Oxygen-hydrogen bonds are polar. The difference is 1.4, right? 3.5 minus 2.1. This is going to be the same situation, okay? And we're going to have a polar covalent bond here. The oxygen still has the higher electronegativity, so it's going to be partially negative, hydrogen being partially positive, okay? And so what that means is that like this region of the molecule is polar. And we're going to talk about what that means later, after Thanksgiving break. Okay? But for today, for today's lesson, and for today's assignment, what you're going to need to do is label polar covalent bonds on structures that you draw. Okay? And you're going to need to use your knowledge of electronegativity and the difference in electronegativity to be able to do that. Okay? All right, well, that's it for today. We'll get some more practice in here after the video, and I'll see you guys afterwards. Thanks.